This is physics, this is art. How do you science that? Shalom, beloved sibling, it is I, Aaron Freeman, not a scientist, but a Sciency optimist, and this week on Physics Friday, we'll be chatting with Nick Gross, the world's greatest living physicist, about the delightful dance of physics and art. For example, in the mid-20th century, the artist Jackson Pollock created some of the most eye-popping and now really freaking expensive paintings of the modern era. Pollock's work was designed not to represent anything in particular in nature, but to show the path his paint took as he splashed it across the canvas. During that same period of history, physicists were beginning to explore the wonders of gas chamber photography, which was designed not to show a particular particle itself, but the path the pieces of that particle described as it was being smacked into other particles. Particle physics also uses many of the terms that we normally associate with art. The quarks that our friends at Fermilab in Batavia are so interested in are described using terms like beauty and charm. Nick says that he finds it difficult to talk about even physics with which he is intimately familiar without drawing pictures. So it's physics and art on Physics Friday here on Science Today. Plus, speaking of Fermilab, we will bid a fond physical farewell to one of the other great physicists of our day, Dr. Leon Lederman, the second director of Fermi National Laboratories. We are delighted to welcome you, beloved sibling, to Science Today Physics Friday with the world's greatest living physicist, Dr. Nicholas Gross, lecturer in physics at Boston University, or Boston University. Do you say Boston?
I haven't developed a natural, I can fake a Boston accent, but I haven't developed a natural Boston. I have to do my park my car and have a yard thing, and then I can get into it. And I can talk about the Red Sox, the Sox are doing, how the Sox are doing, and the Pats, and and I can do the whole, what's his name, the brothers, Wahlberger thing. Yeah, Wahlberger.
So we have an action-packed show today because we are here to talk about something we talked about last week, and the question we asked on Facebook was, does drawing help you think? And so this is the question we're going to try to address here, and we hope that you, beloved sibling, we have one beloved sibling viewing. Thank you very much, and we hope that we will hear from more folks on the interwebs later on as this little broadcast is replayed. But this started out because you, great Nicholas, great professor, were saying last week that even things that you know extremely well when you're trying to teach them, you need to draw on the, hello Tina, you need to draw, but so tell me, why do you need to draw things even though you know them extremely well, but why does that help your thinking?
Well, so I think there's two things going on that part of it is I'm trying to model what the student should be doing when I'm teaching, right? But at the same time, so I don't memorize anything. Okay. I can't remember anything. Like numbers, I got to take them in if I have to copy a number from one place to another, I have to take it in 3-digit bytes. Anything longer than 3 digits, I can't hold that in my brain. So I definitely have to limit my cognitive load. And the way you limit one of the ways to limit your cognitive load,
I'm sorry, I cut you off your sound. One of the ways you limit your cognitive load is?
Sorry, you're asking what the cognitive load is?
Yes, I cut off your microphone.
Yes. Oh, you did.
Nothing personal.
Oh, so I want to limit my cognitive load, and the cognitive load is the amount of information I have to hold in my brain and then process at the same time, right? And so if I'm trying to remember all of the forces that are acting on the object, and then at the same time I'm trying to add them all up to set them equal to ma, because that's what Newton's second law tells us to do. It gets complicated if you got the force that's applied, and the gravitational force, and the normal force, and the friction force, and the force of the string, and the force of the spring, and all these other forces. It just gets hard, right? You can't keep it all in your brain. So you start writing it all. You could write it all down, and then you'd be you'd be writing all these sentences about where the force is and what direction it's in, or you can draw a picture. And the picture encapsulates all of this information all in one spot. And then I just have to look at the picture, and that just makes it suddenly becomes easy. I look at the picture, I write down the equation. So the picture gets turned into an equation for me.
So for you, the picture decreases your cognitive load.
Sure. And then I can handle systems that are more complex.
So so now we were to talk about, when we talk science and drawing, I guess I think we have a picture here from one of the biggies of science and drawing. I believe this would be drawings by?
Charles Darwin.
Charles Darwin. Now, what are we looking at here? And how does this
presumably on the Galapagos Islands, studying finches. So the idea on the Galapagos was that all these finches originated from some poor or a few poor lost finches that happened to make it to the Galapagos very far.
Oh, we had a little freeze on old Nick, but we will say that I am Aaron Freeman, and I am not a scientist, but a sciencey optimist. Nick is going to be right back. Oh, wait, there he is again. You're back. I'm sorry, Nick. Yeah. What'd you say?
Geez. So right, these finches got there by some freak accident, and then all from a single species or a few individuals. They evolved all these different strategies for getting food, and so in order to document that and show people what he's seeing, he's got to be able to draw this, and he's got to be able to explain, here, this is what this looks like, and you notice this beak versus this beak versus this beak. And you could do that with specimens. You could collect your specimens and kill them and keep them safe and like mummify them or dry them out or something and show them to people. But then you can only do that if they have the specimens in your hand. But if you have a drawing, you can publish a book, right? Once they can publish a book.
What's interesting about Darwin is I was talking to I'm forever trying to ask people about their definitions of science. How do you define science? At one point, my favorite definition was the practice of carefully quantifying nature. Mm-hmm. Which I'm sure you like a lot because you people like that. Yep. Our beloved brain buddy, Peggy Mason, says, I think you need to revamp that because Charles Darwin didn't quantify nothing. But I think we all figured that he was a pretty darn good scientist. But one thing we'll get back to later on is that one of the things that art does, one of the things that both art and science does is provide stories to explain the unknowable. Like none of us can see a quark. And we talked about last week that Murray Gell-Mann was figuring them out mathematically long before anybody ever found any sort of experimental proof for them. Mm-hmm. And so art and science try to, in many cases, try to explain to us things that you can't. I see one of those Nick looks like, Aaron, you're off your rocker again. What is this not right? Have I already blown it?
Correct. I'm just trying to I was distracted for a moment. I was trying to catch up. That's what it was.
Oh, okay. Well, like I said, the goal is always to try to get through one of these talks with you without saying something embarrassingly wrong. Okay. So when Darwin drew in order to illustrate, to report, Darwin drew as a journalist. Mm-hmm. To report the science that he had. Okay, what?
I'm trying to think about what that means as a journalist. As a documenter,
Hello, Luane, we love you. So for him, yes. So for him, drawing was a way of documenting his work, as opposed to, as we'll get on later on, visual images that explain things that are otherwise unseeable, or visual images as a way to illustrate something that you will never personally see yourself.
Sure.
Okay. So now let's talk about
right.
What we have right.
Mm-hmm.
Tell us what we have.
Yeah. Oh yeah. So this is interesting. So this is I wasn't able. I didn't have a chance to research this, and I think this is Aristotle and Plato talking to each other, but documented or presented during the Renaissance, and sort of during the early part of the Renaissance, and they had just sort of painters had just discovered perspective, and you can see that this has this is fairly deep perspective, right? So you've got these archways in the foreground and in the background, and you have to assume that the archways, at least in the background, are at least the same size as the foreground, but of course it's in perspective, so they're drawn smaller, right? But we know from our experience that objects that are far away appear smaller, but they could be quite large. And you also see the perspective of the converging walls, right? The walls seem to be coming to a point and so the artists of the Renaissance are starting to play with space. They're starting to explore, how do I represent space? How do I document space? And this is, so the video that you sent me a little while ago, I understand everything that he's saying, and I disagree with him on this one point. He has he's sort of like, there's something in the air at these points in history. There's something around that everybody's breathing. So
let me just say that I sent you a video by Leonard Schlein, and he talked about the first thing he talked about was the Zeitgeist, and that's when you say something in the air that, for example, around.
And as soon as somebody starts trying to explain German to me, I'm like, yeah, whatever.
Yeah,
I'm out.
Fair enough.
Those guys, you don't even know where to put the verb, so
I do understand. But as you say, there are times in history when there's stuff in the air that gets reflected in both science and certainly in the mid 20th century, painting, art.
In art, in literature, Shakespeare starts to develop, starts to show some of these things. He starts to talk about the understanding of that people have, and he starts to juxtapose like the old school mythology, mythos of some of the religious writings at the time to the rational Enlightenment. And Bach comes along. I think Bach is a perfect Enlightenment figure in terms of just like the well-tempered clavier and the fugues, how the fugues come together in this precision that is mathematical and has a pattern to it, and and has patterns and patterns and patterns that then devolve and so so Bach is a great figure to show the Enlightenment.
I'm not quite sure. Explain to me a little more about how that. I understand the fugues, but I don't quite understand how for you that's an appropriate metaphor for the Enlightenment, for the European Enlightenment, mid to late 18th century.
He's extraordinarily creative, but the creativity is inside of a structure that then is, and it's a rational structure. It's a structure about harmony and about and rhythm, and so it's and he's exploring then all these ideas. Okay, inside this structure, what can I make that's creative? And how can I don't know what piece it was, but there's one piece where you take the music and you flip it upside down and it plays backwards. It's what do they call it? when you say a word that you can say it backwards and forwards. Palindrome. Thank you. And
so I think what I hear you saying about the Bach and the Enlightenment is that the Enlightenment is characterized by a rejection of the divine power of king. I mean, there are a lot of things the Enlightenment did, but one of the things that they did was reject the divine power of king and elevate the power of reason.
Yeah,
in a fairly romantic way, reason as the ultimate pursuit of humans.
Right.
And so, that now a little bit before that, a little in the century before the Enlightenment, we can talk about our brother Galileo Galilei, who also he did largely what Darwin did, which was use observation, and he drew what he saw so as to persuade the rest of us that it was real. These are his drawings of the moon that he saw through his telescope. Go ahead, I'm sorry.
Well, and so just going back to what you're sort of trying to define science, I would say to get a broader definition, it's you're documenting, you're systematically documenting what you observe in nature, and you do it in a way that other people can follow your steps.
I can't believe a physicist would say this. If you think that the rest of us can follow you, we're going to show here some Fineman diagrams. If you think that the physicists document nature in the way that the rest of us can follow, I got a bridge for you, my brother. Are you going to stick by that?
I said someone can follow, and someone, but also presumably someone who's, of course, had, you have to go through certain experiences to be able to work at CERN, right?
Yes.
Or be able to, but at the same time, going back to like Darwin or Galileo, right? I can get a 3-inch refractor telescope and look at the moon and draw what I see.
Right.
Okay. And now my drawings are going to be pretty poor. So one of the things I would have to learn how to do in order to do that is draw, right? So you might have to learn a little quantum field theory, and I would have to learn how to draw if we wanted to follow.
I think I would have to learn a lot more. Well, quantum field theory, I can barely pronounce the term. Okay, I'll say. But now I'm curious about here. Was another drawing that you had suggested was indicative of something substantial, and tell me what this means to you.
So this is DaVinci, right? So DaVinci I think this is from DaVinci's notebooks. That's where I was like, and it's just another way of like, he's got a vision for how this thing's going to work. But, with any of these visions, whatever these mechanical device is, and this is some sort of a shaft that's being run by a wheel, and whatever this device is, he's got to show you how to take it apart and put it back together again. So he's got so on the right-hand side is I believe is the completed device. And it's got a little rock that's falling here, driving this wheel, which then drives the bigger wheel, right? And that's on the right-hand side. On the left-hand side, it's the exploded version of this. It's the exploded diagram, right? So this is sort of one of the early mechanical drawing exercises.
So what's interesting about this begins to get at what we were talking about art and science showing us things that we could not see, because the exploded drawing is and so the other thing what this does that we didn't see in Darwin or in Galileo was that this is not precisely what anybody ever saw. This is how he imagined it would work. So this was art to expand that which could be seen.
Sure, right.
Because anybody with Galileo's telescope could have seen his version of the moon, and anybody who'd gone to the Galapagos could have seen what Darwin saw. But an exploded version of a mechanical device is not something that you could just access by looking at.
No, that's a great point. I absolutely agree. Yeah, you can't access that. You can't see how to take it apart and put it back together again. You can't see how to build it. right? So now you've got to
Yeah.
build the thing, and you've only, and without the exploded version, I wouldn't quite know what to do.
Yeah. So this is again, this is the showing of things that are invisible,
Right.
which
Right.
is also what well, not the showing of things, but the imagining of things you can't see. Now here is where we humble old Aaron. I know what it is. I don't know what it means. Please tell us, what the heck is this?
So these are referred to as Fineman diagrams, and these are some pretty complex Fineman diagrams.
Wait, who? Fineman? Fineman?
So Richard, they're named after Richard Fineman, so a Nobel laureate in physics in the mid 20th century, solved the electrodynamics. Basically, solved the. He was able to complete the theory of quantum the quantum field theory for electricity.
Right.
So and sort of wrap that all up and put a nice neat bow on it and say, okay, we're done with this now. We don't have to touch it anymore. We've explained everything. We've developed all the theory that explains all the phenomena that involves this piece of physics.
So this this is a real serious example of drawing that gives us a glimpse of something we are not going to see.
Well, and these drawings aren't supposed to represent what's actually going on. They're models that you use then to. They might represent some idealized version of what's going on, but they're really models that help you, as I said, help you do calculations. So each one of these drawings can be turned into an equation. And oftentimes what you have to do is piece the drawings together. So you have to add the terms that each drawing represents together in the equation. And then you get ultimately the probability that you're going to get some two electrons are going to come in and bang into each other, and you're going to get a photon out. So
what is the utility of a drawing like this over an equation, which I wouldn't understand?
So it's a matter of bookkeeping. I would say, right? So it's a matter of saying, okay, I've got and have I counted for all the permutations of the way I can draw this? So there's different variations on the drawing that you'll have to do. It's been a long time since I've thought about this, but it was but what you have to do is you have to, like, in each drawing, you add a little bit to, or you either change something, you do a permutation, or you add a little bit to it. And so each drawing, in fact, each drawing here, you see the left-hand side of the drawing has two electrons coming in. I think it's not very big, so I can't see it all, but two electrons coming in. And then on the right-hand side, you got two electrons going out. Whoops,
I see it. I see that. Yes, you're still on.
Yeah, no, I'm trying to zoom in, and I can't get it any bigger. So I'm
on the left. You have two electrons coming in. Those two figures on the left are electrons, and on the two figures on the right side of the screen are electrons going out.
Well, on each of those diagrams, so there's two.
Okay, got it. Okay.
10 diagrams, okay. Right? So you've got electrons coming in on each diagram. You've got electrons coming in on one side. I can't do it. And electrons coming in on one side, and electrons coming in on the other side. And
okay.
And so, and in between are different things that can happen to those electrons. And so, and you want to document all the different possibilities of things that can happen to those electrons. In between seeing one coming in and one coming in this way and one coming in this way. And so
So I am Aaron Freeman, and I'm not a scientist, but a Sciency optimist. We are here on Physics Friday with physicist Nick Gross every Dat Blame Friday afternoon, whenever Nick's schedule permits. But yes, I was just, while you were frozen there for a little bit, I was filling in to remind our wonderful viewers and thanking them so much and hoping they will come back and join us next Friday. Now, we talked last time about something that we have some art to represent. The fluidity of space-time. This is one of the most famous paintings by
Salvador Dali.
And so tell us, what you as a physicist, what you looking at here, blah?
Well, I want to go look up. I don't know when so this is the persistence of memory. Persistence of memory. I want to get a date on this. So this is not until 31, which is interesting. Okay. But
it's still within that same time frame that Pollock was working, and they were doing those gas chamber photos. Cloud chamber photos. Gas chamber is a whole different thing.
They wouldn't have been doing them in 31, I don't think.
Yes, no, you're right. But in the 50s, they were doing those.
In the 50s, yeah.
I'm saying, speaking of Zeitgeist, in the same general period of time. So, but as a physicist, so in 1931, we're seeing this. So, what does this mean to you? How does this relate to our many discussions about?
I don't know for sure. My art history is a little weak on this, but I've always thought that this is related to relativity. This is related to special and general relativity, where time is just a metaphor for time and space being warped and twisted and turned, and that you can take these watches and just let them sort of drape as they will in different ways, and fold that space and time and turn it on itself, and it just was interesting to me to realize that it's a little bit later than Einstein, but it's not that much later than Einstein. It's in the 30s when they're really starting to play with some of these, breaking all of the old conventions. So
now, I assume that the space-time implications of a picture like this, with time melting and stretching, would have been lost on all but the most cutting-edge physicists. No?
Certainly not in 1931. By that point in time, many of them were fully aware of relativity and its implications. And I think it had gotten into the again, it's in the air, right? It's in the ether. You just start sniffing around. I mean, at that point in time, Einstein is a celebrity in a way that you might or might not want to be. And he is, and so people are at least trying to wrap their heads around some popularized version of his work. I have a book from 1915 that he wrote that was an attempt to popularize it. I don't recommend it, but I have it. And so he was somebody once asked Einstein how radio works, and he said, "Well, you know how when you pull on a cat's tail it meows? That's how radio works, except without the cat."
Okay,
I'm like,
I like that.
Dude, is that the
well?
best
Now speaking. Now, in that same period of time, speaking of Zeitgeist, once again, in the mid 20th century, we have the work of Jackson Pollock.
Yes. And
what was so interesting about this is that Pollock's work. I read somewhere that Pollock working. His working process is among the most displayed of any artist.
Oh,
there are more pictures of him doing what he did, and what his works was sorry. Okay, his work were a record of the motion of his paints and brushes across the canvas, which plays interestingly into our physics brothers and sisters. So let's see, get that down there, get rid of that there, because we later, as I mentioned, this cloud chamber photography, which is this, which also is a record of the motion.
Right.
Of things that we could not see. Like we couldn't see Jackson Pollock working, but his paintings were a record of what did happen on his canvas, and we can't see. I'm not sure what this one is, but this is very familiar to those of us who like follow these kinds of things. It's a record of the motion of particles as they smack into one another.
Right. And so this is and it's the record of motion of usually of the particles that are left after something's done the smacking. Right. So I have to carefully.
This is like a leftover particles, or motion of particle pieces.
Well, that's exactly what you had to do, right? You had to have a lot of trained help, usually women, looking at these pictures to try and figure out, identify all the individual tracks in the photograph. So these are particles that were passing through what's called a cloud chamber. So it would pass through a vapor, or not it's actually really not a vapor. It's just very moist air. Usually you didn't use water, you used alcohol, but it was super saturated air that was very cold. And as the particle would pass through, it would leave a trail behind it that the vapor would collect on near where the particle passed, and it would condense, right? And then you get a quote unquote little cloud that would follow the trail. And so and if you've there's nobody does this anymore because people kind of frown on having like open radioactive sources around, but
what a bunch of wimps. OSHA.
But I've done this in the past. You take some dry ice usually, and you moisten with some rubbing alcohol. You moisten the bottom of a petri dish that's covered in like paper, and so you let it evaporate, and then you cool it pretty quickly, and then you put a little a radioactive source, and you'll see coming off of the source, just little clouds will suddenly appear out of nowhere. It's kind of magical and a little scary.
Well, now speaking magical and a little scary, Lonnie mentions the Starry Night.
Yeah.
And what's interesting about that is, of course, when most of us look at stars, we see dots of light.
Mm-hmm.
Did not he saw swirls of light around? I mean, his view, what he saw and the way he drew stars was, I would say, closer to what science is, to what the actual astronomy was, because they're not merely little dots. There's all kinds of stuff going on around celestial bodies. They have, like stars have atmospheres.
Right.
And,
right.
And swirls of radiation, and they move in spirals through space, much more close, because for us, they look like fixed points in the sky. That's what Ptolemy thought. I'm sorry, go ahead.
No, I'm here.
Yeah, no, I thought I was, but yeah, so that.
No, I was looking up Van Gogh and just to get it.
Starry Night.
Yeah, right.
A really, a very different, got a very different view of stars, and much closer to the astronomical realities than we poor non-artists get to have.
Yeah, and I don't know what he was trying to depict there, whether that was that was intentional, or did he have some form of what's the thing, some kinesis, where you see
clairvoyance?
No, you see colors. Sorry, you see music. Or
synesthesia.
Synesthesia. You're right. Where there's something going on there. I don't know. But
Well, Vincent was a weird guy. Vincent was a definitely. I mean, you and I are a little strange, but Vincent was acutely odd.
ow,
Yeah, he was.
that one. I forget which.
Yeah, but I would say that we're pretty much pretty normal people compared to Vince. So, as we tell me, what do you get from? You obviously are a pretty art literate kind of guy. Does the art that you have watched influence the physics that you understand? Like when you see Dali's depiction of time stretched and dripping, does that help you to design metaphors for space-time that is useful in explaining it to non-physicists like me and your students?
Maybe, I'm not sure. I think I see when I see art, particularly when I listen to music, and I understand. I mean, I both understand music, and I understand the physics of sound, and I understand the physics of musical sound, right? And we can get into pitch and intonation, and pitch and timbre, and the frequency spectrum, and harmonics, and understanding. This is where Bach comes back, understanding the relationship between pitch and frequency, harmonics and harmony, and chords, right? That chords that sound good together all have the same harmonics, have share, or that not the same, but they share harmonics, right? So the notes in a chord all share harmonics, and that just like makes me all giddy inside.
Well, what I think I hear you saying is really one of the things that I really deeply, profoundly believe, which is that some understanding of the physics of the world, of the various sciences of the world, can make that world, your appreciation of that world, more richer. You know, I say more science, more happy, and because you understand how sound waves work and how pitch works and how frequency works, that makes your musical experience richer, deeper. It gives you more cool stuff to appreciate about the music.
Right. And I think there's like a stereotype of a scientist who just dismisses, like somebody, they see a rainbow and they dismiss it as, oh, that's just refraction. It's like, no, that's really cool.
No, that's refraction, man. Refraction. You know how
internal reflection, and it's all of these droplets working all at the same time. And if I look in the right spot, I mean, we've talked about this before, that there's this deeper. My sense of the world is, I feel like it has a deeper appreciation of the world, of the physical world, because of my understanding of science. And I can go around, and that's true about not only physics, but my understanding of biology. I can go to a beach in Hawaii who has black sand on one side, white sand on the other, and a mixture of black and white sand in the middle. And the crabs on one side are black, and the crabs on one side are white, and the crabs in the middle are speckled. And you're like, aha.
Yeah. So, I mean, so that again, your understanding of, well, this is similar to the business about Dali and his melting clocks, that your understanding about space-time gives you a whole new way to look at and appreciate Dali's art.
Yeah, I have no idea what he meant, but that's what I get out of that.
Yeah, well, it gives you a different way to look at it. It's not even you haven't got the ultimate answer to it, but it is.
I'm always right.
Yeah, it goes without saying that you and I know you have the ultimate answer even beyond 42. But why would you share it with us? You want to save it for the tuition-paying students at Boston University. But so we're a little over our normal time here, but I do want to take one quick second to mention that this week the physics world lost one of its greats, Nobel Prize-winning physicist Dr. Leon Lederman, who I not only met and interviewed several times, but there's somewhere I couldn't find it. But there's even a picture of him with my kids. It was a very, very
wow.
Like so many physicists, he was a very funny guy, very entertaining, and he was the second. He was instrumental in the founding of Fermilab and was its second director. And to the Letterman family, we used to say, "Good job, you guys! Great genome you got."
And you know, at the same time that we lost Leon Letterman, we gained another Nobel Prize winner because the new Nobel Prizes, among the three who were awarded the Nobel Prize in Physics for their work in lasers, was Donna Strickland, from University of Waterloo in Canada. So
there have not been a whole lot of Nobel Prizes in physics that have gone to women. 3. Okay. And so this, Donna Strickland, we send our
yes,
way to go. It's yes. Well, that's really fabulous. So we are past our time, but it is so wonderful to spend time with you, my dear. The time went fast.
Yes, it did. Always does with you, Aaron. You make time.
Well, you know,
it's you must be moving faster than.
Well, of course, it's all relative, Nick.
It's all relative.
So
we're here all week, folks. Don't forget that.
That's right. So we want to thank Luani and
thank you, Luani.
And Trish, Tina, for Tina, we thank you so much. Thank you. Well, it's been fun to have you here, Tina.
Oh, great. Yeah. Fluid dynamics.
Yes, fluid dynamics. There's a whole art in fluid dynamics and the depiction of water in paintings and Monet. Another wonderful topic. We could go on and on and on. But right there is my dear brother, not merely my physics coach and worst nightmares, since he knows all this stuff that I'm popping off incorrectly about, but my fellow improviser, Professor Nick Gross, lecturer in physics at the University of Boston, and Boston University, not University of Boston, Boston University. And we love you guys very much. And so hopefully we'll see you next week, and we'll have an even more faster moving, more fun time with our Physics Friday.
Okay. Yes,
right,
that would be great. I'll look forward to seeing everybody on Friday.
All right. See you soon. And thank you guys. And I hope it's the best weekend of your lives.